All right, so now we're going to discuss the law of large numbers in our study of probability. The law of large numbers is a way that we can see what happens in our samples as we get larger and larger samples and how they're better able to show us what goes on in our population. This is how probability supports what we do in statistics. So now let's take a look at this. When we did our classic approach, right, our classic approach to probability told us that the probability of flipping a coin and getting a head was going to equal 1/2. So that's the probability of a head was equal to 1/2. Now, when we did it with relative frequency, right, our relative frequency approach, our relative frequency approach told us that this probability was equal to 1/3. And we know that that's not accurate. We know that when we flip a coin, or at least I hope you know, that when you flip a coin that you will actually see it a head come up half of the time. But why do they differ? Well, the classic approach tells us in theory what will happen, and the relative frequency tells us what happens in a sample. So that's why what we're seeing. So what I've done is I've used my Mac and I've used Excel to generate different numbers of samples of flipping coins. So I didn't sit here and flip my coins for real. I did it using a simulation. Now we could do that simulation with our TIs. We could do it with a random number generator or a random number table. We can do it a lot of different ways, but I chose to do it on my Macintosh. So we have here the probability of H sub 20, meaning that I've symbolically flip the coin 20 times, right? That's what I've simulated. And in those 20 flips, I got 11 heads, and that gave me the probability of a head of being 0.55. And then I did it, and I did it for 25, and for the 25, I got 8 out of the 25. And then out of 30, I did 12. I got 12 out of 30, and out of 35, I got 9 out of 35, and so on and so forth. And you can kind of see that down here, it's bouncing all over the place, right? Up and down. It's almost right on, it's low, it's not quite as low, it's really low, it's not quite as low, it's really low, it's really low, it's not quite as low, it's almost there, it's a little bit high, it's almost right on. It kind of bounces, 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 bounces. And then what you start seeing is you start seeing around, it's usually somewhere in the 75 plus range, you start seeing it kind of settle down to be right at the 0.5. And that is the law of large numbers in action, and that's what's happening. So what I see here is the law of large numbers taking a hold. So as we have a small sample, the probabilities according to relative frequency probability can kind of be all over the map, right? But as we get larger and larger samples, the probability from relative frequency settles down to be right along this 0.5, which is our theoretical probability. And that is exactly what happens in samples. As we get larger samples, we are more and more able to see what's going on in the true population. And that, of course, is if we don't have any non-sampling errors going on. So here's our law of large numbers stated. It says in the long run, as the number of trials increase, the sample size increases. In other words, the relative frequency probability will approach the theoretical or classic probability. So now we're going to go ahead and we're going to move away from the law of large numbers here, and we're going to start seeing some of the things that we were talking in our set theory. And so the first thing that we're going to talk about is our complement, the thing that I had discussed prior. So we're going to discuss the concept of this complement as being A with a superscript, a C, or A with a bar over it, right? This is typical notation, the A with a bar, A with the superscript of C being easier to write. And we're going to talk about the probability of the complement as being equal to 1 minus the probability of the event. Now, of course, This means that we do have mutually exclusive events. That's what we're talking about when we're talking about complements occurring. So, for instance, if we have heads and tails, there's no overlap here, right? You either get a head or you get a tail. You don't get somewhere in between. It's either or, one or the other. So we can talk about event H, and we can talk about event H complement, or H complement written with the bar. And this, of course, is equal to getting a tail, right? So if H is a head, then the complement of getting a head when you flip a coin is getting a tail. And so those are the things that we can talk about. And that's what we're going to look at in our next example. Our example says if we flip a coin 1,000 times and 613 heads appear, what's the probability of getting a tail? So you see I've defined the events here. A is getting a head, and A complement is getting a tail. And that's because A union A complement is equal to the sample space. In other words, everything here, right, that's all there is. And so if I have the probability of A is 613 out of 1,000, or 0.1613, then the probability of getting a tail, the complement of getting a head, is 1 minus the probability of getting a tail. And one of the things that you'll notice if you write this out, and let me just write this out longhand for you because you might not realize that this is what you're doing, but you're doing this computation. And one of the methods for doing this computation is the good old long way, right? Which is to say I have 1, which is represented by 1,000 1,000ths, minus 613 1,000ths. And the way you do fractions, remember, is you subtract the numerators and you put them over the common denominator. And when you look at that subtraction of numerators, isn't that exactly what you expect to do when you're finding how many tails you're going to get? Well, if I got 613 heads, then I must have got 1,000 minus 613 heads, or, and this number is actually wrong here, this should be a 3. Keep forgetting to change that. So this one should look like 387 tails, right? We got 387 tails out of this. So that is a 0.387, and that's exactly what you got. Why don't you go ahead and see if you can do this next problem on your own. So just go ahead and pause your computer, or pause the video, and go ahead and see if you can write out this problem. 10,000 people are surveyed and 2,500 people are found to like a product in question. What's the probability that a person does not like the product? Use the complement to find this probability. So what you should do is try to write it out notationally and everything. I am very big in my classes on notation because the notation helps us to understand as a group what it is that we're talking about. So go ahead and pause your video and go ahead and try to figure that out. Okay, hopefully you took my advice and went ahead and paused your computer. So I'm going to go ahead and I'm going to define as L, that's liking this product, right? So this is like the product. And then I'm going to define not L as don't like this product. And so now I'm going to say, okay, well, the probability of liking the product based upon relative frequency probability, right? If I have 10,000 people that were surveyed, that's my N, and 2,500 of them do indeed like the product, then I'm just going to simplify this down. That looks like 2,500ths, or 0.25. If you prefer, you could write it as a quarter, right? Either one. So that is my probability of liking it. Well, then if I want to know the probability that you don't like it, then that would be 1 minus the probability that you do like it. And that would look like 1 minus this 1/4. And we should all know, because of money, that that's equal to 3/4, or 0.750. And so that's the probability of not liking it. That's the complement idea right here, right? This is the complement that we were talking about and we had defined. We had defined that in terms of set theory, and now we're using it in terms of probability. And you see the way that we had used it in set theory was what happens in our numerators here, right? Because this is 1, which represents 10,000 out of 10,000, and that's minus the 2,500 out of 10,000. And what goes on is in our numerators we subtract these numbers, right? And out of 100,000, if 2,500 of this, that leaves 7,500 that are of the other type, doesn't it? And if that's the case, then exactly what we said it would be is what happens, 75 out of 100, which is what we saw right there. And so what we were talking about in terms of set theory is what happens in probability as well. All right, now moving on, we're going to talk about the odds against an event occurring. Some books will go ahead and talk about the odds for an event, but odds against are a little bit more popular. So odds against event A. I think it's best that you start by defining what odds you're talking about, right? So what is the event that you're talking about? And from there you can kind of build around it. So odds against event A looks like the probability of not being A divided by the probability of being A. Now, because these are ratios, we can talk about them like that, or we can talk about them like this, as a ratio is written with the colons. So either way is acceptable, but because we are dealing with probabilities, which are numbers, we tend to revolve around this fractional representation. Now, one of the things that we note about this fractional representation is that if you add the numerator and the denominator, and that's what this says right here, if I add this and this, that's going to tell me the number of ways that it can occur, right? This is the total number of trials, in other words, the number of simple events. That's another way of looking at if it's classic probability. But usually we're going to come across these not from classic probability, but usually from a relative frequency. So this would be this P of not A and P of A. What we're going to be seeing in the odds is just going to add up to be the total number of trials. And the number on the top is going to be the number of ways that the complement will occur, and the number in the denominator will be the number of ways that the event itself will occur. And that's, again, what these facts say. So let's just decompose that in a little bit different way here. So the odds against selecting a left-handed person are 9 to 1. So the odds against a left-handed person are 9 to 1. So what this tells me is that out of 10 people, 9 will not be left-handed, and 1 will be left-handed. And that, again, is exactly what we were talking about in these three things here, right? 9 plus 1 is saying that out of 10 people, and the top number being not left-handed, and the bottom being the left-handed people. So that's what these first three represent. And then we can put it back in terms of probabilities. So the probability of being left-handed, that is the 1 out of the 10. And the probability of not being left-handed, right? Probability of being right-handed as being not left-handed, that would be equal to 9 out of 10. And that's where we'll end for now.